A frustum is made by removing a small cone from a mathematically similar large cone. That is, the cones are in proportion, one is a scale factor of the other. Work out the volume of the frustum shown. So the way we're going to do this question is we're going to work out the volume of the large cone, and then we're going to take away the volume of the small cone, and that will give me the volume of the frustum as my answer. However, to do this, I need to refer to the formula for a volume of a cone, which is on page 2 of the exam. So, let's start by working out the volume of the large cone. Now, to work out the volume of the large cone, the variables I need are the radius and the height. Now, I haven't got the radius, but I have got the height. The height is 40. But I can clearly see that because the diameter of the large cone is 30, I know that the radius of the large cone would be 15. And now I can use those numbers in my formula. So my large cone, my volume is 1/3 times by pi times by radius squared times by height, and the height is 40. I can do this on my calculator to give me an answer of 9424.777961 centimeters cubed. Notice how I have not rounded or done any estimations there. It is an exact number because my answer needs to be exact at this point. It's only part of my calculation. Now I need to work out the small cone. Again, the variables I need for this are the radius and the height. Now, I know the height of the small cone. That's very clearly shown as 20. Now, the radius of the small cone isn't given to me, but I can work this out very easily. Because the height of the small cone is half of the height of the large cone, I know that the radius of the small cone is half the radius of the large cone. Therefore, the radius is 7.5. So the volume of the small cone is 1/3 times by pi times by 7.5 squared times by 20. And that's by substituting it into the formula, the same formula I've been using throughout this question. On the calculator, I get an answer in terms of pi, but I'm going to choose to use it in terms of numbers, so I get an answer of 1178.097245 centimeters cubed. Okay, so that's the small cone, and I know the large cone, so all I need to work out now for the frustum is to do the large, take the small. Okay, so the large cone, take away the small cone. And again, I haven't got room to show that working out, but I'd certainly do that on the exam paper. And when I do this on my calculator, I get the answer of 8,246.680,716 centimeters cubed. Again, I've not been asked to round it, so I'll not round it. Okay, here's an exam question for you on this. There's an additional part B, which could be something you'd be asked in the exam, and I'll let you have a little think about that. But part A is very similar to the one beforehand. I think you need to work out the height of the large cone, though, first of all. Pause before you want to see any part of the answer. So you'll see that what was key here was working out that the height of the large cone was 10 centimeters, double the 5 centimeters, and that's because the radius was double, so therefore the height must have been double as well. So the volume of the large cone, 1/3 times pi times radius squared times height. Small cone, same formula, using the numbers in the small cone, and the frustum is the large, take away the small, which gives me this answer. In terms of part B, where you need to work out the total surface area of the frustum, this is a much harder question. Only in that I've got more calculations to work out. The way I'm going to do it is to work out the curved surface area of the frustum. I'm going to then have to add on the round circular area at the top and the round circular area at the bottom. Now the circular area at the top and bottom are relatively easy to work out. In terms of the curved area of this frustum that goes round the shape, I'm going to have to use the other formula which is given to me. I'm going to have to do the same as before, where I work out the curved surface area of the large cone, take away the curved surface area of the small cone, and that will give me the surface area, the curved surface area of the frustum. Now to do that I'm going to have to do Pythagoras, just like on the cone question, which is why this question is a much more involved question. So Pythagoras on the cone lets me work out that the diagonal length of the large cone is 11.66. That's using the height of 10 and the radius of 6 on that right angle triangle. When I substitute this into the curved surface area formula, I get an answer of 219.786. I'll have to do the same now on the small surface area. So as you'll see here, I've had to do Pythagoras on the small triangle to work out this diagonal length. And then when I substitute that into my curved surface area formula, pi times radius times diagonal length, I get the curved surface area of the top cone. Just like before, I'm going to do the large take away the small, and that will give me this curved surface area of the frustum. And finally, as I mentioned before, I now need to work out the surface area of the base circle and the top circle, and that will give me the total surface area of the frustum. So all of this working out was to give me the curved surface area, and now we need to work out these two faces as well. And finally, my answer of the total surface area will be the curved surface area of the frustum at the top circle, shown here, add the bottom circle, shown here, which gives me an answer of 306.21 centimetres squared. Now that's a lot of working out for that question, and I wouldn't particularly expect all of that to appear on the paper, but certainly the methodology behind it and the logic behind it certainly applies to any type of question.